Hello everyone, this is Zhe Wong from the Vela team at Xiaomi. I am excited to participate in this year's NuttX online workshop. I joined the Vela team in September of 2022. You may see me appearing in the NuttX community from that time on. Time flies and a year has passed, and today I will present on the topic of NuttX Network Subsystem Enhancement Overview. In my presentation, I will discuss some of the enhancements that have been made to the NuttX network subsystem in the past year. Here comes the agenda, which consists of three parts: the network structure enhancement, the functionality enhancement, then the landed products and future work. Let's start with the network structure enhancement. There are three enhancements I'd like to share: the user sock RP message refactor, the LB offload, and the upper half driver of network devices. First is the user sock RP message refactor. So what is user sock? It stands for the API for the user space networking stack on NuttX. Vela uses user sock with RP tunnel to share networking between cores, because Vela may run differently configured NuttX on different cores, but they all need access to the internet. As shown in the figure, we may design products using a core with a full network stack as the server, while other cores may access the internet by using UserSock as a proxy. The UserSock RP message client will relay the socket requests to the UserSock RP message server, and the server side will do the actual work by its network stack. But we noticed that the performance will be dropped around 25% to 40% on proxy cores compared to the main core, which is running the UserSock server. It's an obvious decrease. Can we optimize this? Of course, we can optimize this. Let's first look at the current workflow. When an app on cores using UserSock as a proxy wants to access the network, its socket operations are handled by the UserSock interface and sent to the UserSock device. Then there is a UserSock RP message client thread who is always polling the device to get these socket operations. The UserSock RP message client will send these socket operations as UserSock requests to the server core by RP tunnel, which also has its own thread. When the core running UserSock RP message server receives the UserSock request, it will post this message from the RP tunnel thread to the UserSock RP message server thread, and then the final socket operation is generated and the actual network-related work will be done in the net driver thread. The performance issue comes from two parts. One is there are too many threads involved in this workflow, which causes a heavy context switch overhead. Another is that we can only get one single packet per request. Then we may optimize it by, first, remove UserSock-related threads and make them become modules. Then these modules will be called in corresponding threads, like the driver thread, the RP tunnel thread, or the app thread, to reduce scheduling costs. In order to do this, we combined the UserSock interface directly to the UserSock RP message client on the client side, and introduced the poll callback mechanism on the server side. Also, we changed the workflow to support transporting a bulk of data in a single request to reduce the latency. After these optimizations, we've got an improvement on the performance of our products by 18% to 41%. Also, after splitting the UserSock device from the UserSock interface, we can support more types of backends more easily. We've seen the UserSock driver on the NuttX simulator drop dependency on the UserSock device, And some applications like NRF91 modem sockets also connect to the user socket interface directly without attaching the user socket device. The second enhancement is the LB offload. The LB stands for the L buffer, which is widely used in our network stack. As the driver structure shown in the figure, our network driver allocates the buff, which is the driver's own buffer, and gives it to our network stack. But some parts of our net stack will use L buffer instead. Then there will be a copy between them. The LB offload mechanism lets the driver also use LB instead. Then we'll always use LB from stack to driver. So in most cases, there will be no copy between the driver and the network stack or inside the net stack. Since our buffers in the stack, like send or receive buffers, normally consist of LBs, they may benefit from LB offloading. We also have some other cases which may benefit from offloading, like we can just relay the LB from one device to another in forwarding cases. On the driver side, sharing buffers instead of allocating its own buffer may reduce memory usage in some cases. And it's easier for the driver to get multiple buffers for parallel execution. By the way, we also have a compatibility layer for previous drivers to keep working correctly under the new structure. The LB offload has been applied to several network drivers like the simulator of NuttX, the ESP32, and the virtual I/O network driver. And we may see significant improvements in each case. The third enhancement is the upper half driver of the network device. We found that in our network device drivers, there seems to be too much duplicated logic. Take transmitting as an example. When the net stack wants to send a packet, it calls on TX notify, which will trigger the driver's TX available method. Then the driver needs to queue its transmitting work into its own thread or a work queue like LP work. Inside the transmitting work, the driver needs to prepare a buffer and call devwithPoll from the net stack, which will call back to the driver's transmitting method TXPoll to do the actual transmission. This is such a complex workflow that our vendor who wants to adapt a driver needs to know our work queue or threading mechanism clearly, as well as our network stack interfaces, like devwithPoll, or maybe some input interfaces of net stack in receiving workflow. To simplify this, we introduced the upper half driver, which implements the common logic of this work, and hides the queue, the thread, and the interfaces of the network stack from the lower half. Then the lower half drivers may just pay their attention to the transmitting or receiving operations. We've added the upper half driver as an optional module, which doesn't influence previous drivers. You can use the upper half driver whenever you want. It has already been applied on several network drivers, like the network driver on the NuttX simulator, the virtual I/O network driver, and on some net drivers on Vela products. In practice, we found the upper half driver may save around 35% to 60% of the code lines of each driver, and we have designed the interfaces to make adaptation of LB offload easier when using the upper half driver. After introducing the network structure enhancements, let's continue with the network functionality enhancements. There are also 3 enhancements in the past year I'd like to share: the network address translation, the IP fragmentation and reassembly, and the TCP selective acknowledgement. The first functionality is NAT, which is short for Network Address Translation. NAT is used for mapping a group of IP addresses to another group of addresses. NAT is widely used on home gateways, and you may have one in your home with several LAN ports and a WAN port. It translates IP addresses on the LAN side to the IP on the WAN side, so all the devices on the LAN side share the address on the WAN side. This process is also called IP masquerade. We already have IP forwarding on NuttX to support routing between multiple devices. Maybe we can become a home gateway. So we added a NAT functionality. As shown in the figure, we call the addresses used by user devices as local addresses. We call the address assigned to the WAN device of NuttX as external address. Normally, the external address will be a global address. When a user device with a local address wants to access a public server, it will create a connection that uses the adjacent port of the device as the local adjacent port, and set the adjacent port of the public server as the peer adjacent port. When this packet is forwarded by NuttX, the NAT will try to find an entry that maps the local adjacent port to the external adjacent port, and accordingly change the packet. Then the server will just see the packets from the external adjacent port and reply to the external adjacent port. When NuttX gets the replied packet from the server, it changes the external adjacent port back to the local adjacent port and forwards it to the LAN side. Then the communication can work correctly. We have considered the case that we have multiple WANs or LANs, so we just put NAT logic before and after the routing logic of NuttX. Then packets can be routed correctly, and we may have multiple LANs and enable NAT on multiple WAN devices without any problem. As I just mentioned, an entry is used to map from a local IP address and port to an external IP address and port. We can support a limited number of entries, which means we can support as many connections as we can until we use all of our port numbers on each IP address on one side. These entries are saved in a hash table, so the performance of NAT won't decrease a lot even if we have thousands of entries. A command line compatible with IP tables on Linux is also added. We use the interface compatible with Linux and implement our own logic behind it. Although we only support the masquerade target now, we may add more functionality later. The next enhancement I'd like to share is the IP fragmentation and reassembly. On each data link, we have an MTU, which is short for Maximum Transmission Unit and stands for the largest size of a single frame or packet across a data link. So what if we want to send a packet larger than the MTU? The IP fragmentation mechanism helps us. Let's put our eyes on the figure. When we want to send a packet larger than the MTU, we may break it into smaller fragments, so these fragments are small enough to be transmitted successfully to the receiver. Then the receiver may reassemble them back to the original big packet and process it correctly. This is how IP fragmentation and reassembly works. The support of IP fragmentation and reassembly has also been added to NuttX in the past year. The last enhancement I'd like to share is the TCP selective acknowledgement. Let's see a common case we may meet in TCP transmission. When a sender sends several packets, but some of them get lost in transmission, the receiver can only reply acknowledgement on one sequence number to indicate there might be a packet loss on the wire. But relying purely on the cumulative acknowledgement scheme can lead to inefficiencies when packets are lost. So how to optimize this? The SAC may help us. It's an option in the TCP header, which can help the sender to know about holes in the receiver buffer at an early time. As shown in the figure, the receiver may save received packets in an out-of-order queue and use the SAC option to tell the sender which packets it has already received. Then the sender will know where the holes or lost packets are and can retransmit them earlier than the normal retransmission mechanism using timeout. After enabling the TCP selective acknowledgement mechanism, we get a great improvement in performance when we have packet loss in transmission. The performance tested on ESP32 shows that we increased from a very low throughput to a throughput close to the original performance without packet loss. These are the enhancements we have done for the NuttX in the past year. And finally, I'd like to share some landed products during the past year and a few future works we are planning on the NuttX network subsystem. The Vela team has landed several products with network support during the past year, including IoT modules, smart speakers, watches, smart bands, and some other categories. They are all equipped with the newest network features and benefit from these features. Finally, it comes to the future work. First, we may still keep improving our network stack and the behavior of sockets. We have used test cases from libuv to help us improve our socket behavior. In the past year, the pass rate of these socket-related test cases has increased from around 30% to 83%. Besides looking into the rest of the cases, we will also try to find other test suites that may help us improve our sockets. There are also some features under planning, like simulating Wi-Fi operations on the NuttX simulator or the Wi-Fi based on virtual I/O, so we can run apps requiring Wi-Fi operations without an actual device. And we are going to implement or transplant protocols like IPsec and Matter to help us go further in the field of the Internet of Things. That's all of my presentation today. Thanks for your time.